Welcome! In this session, we'll explore problem number 1604, alert using same keycard 3 or more times in a 1-hour period. This problem challenges us to identify employees who use their keycard excessively within a short time frame, which could indicate suspicious activity. Let's dive into the details and examine the approaches to solve it. In this problem, you are part of a security team for a corporation that monitors keycard access to secure areas. Every time an employee uses their keycard, the system logs their name and the time of access. The challenge is to identify employees who have used their keycard 3 or more times within any 1-hour period. If an employee meets this condition, they should receive an alert. Your task is to implement a function that processes these access records and returns the names of employees who should be alerted. The names must be sorted in lexicographical order. The input format consists of a list of access records, where each record is a string containing the employee's name and the time in the format HHMM. The output is a list of names that meet the alert condition. If no one qualifies, the function should return an empty list. Let's consider the first example. The input consists of two lists, keyname and keytime. Here, the records show that Daniel used his keycard at 10:00, 10:40, and 11:00. These 3 times fall within a 1-hour period, so Daniel receives an alert. On the other hand, Luis used his keycard at 09:00, 10:00, 11:00, and 12:00. While Luis used his keycard multiple times, there isn't any group of 3 usages that fall within a 1-hour window. Therefore, Luis does not receive an alert. The output for this example is a list containing just Daniel. Now, let's review the second example. The input lists show that Alice used her keycard at 12:01, 12:02, and 12:03. Since all 3 times are within a 1-hour window, Alice receives an alert. Similarly, Bob used his keycard at 03:00, 03:01, 03:02, and 03:03. The times 03:00, 03:01, and 03:02 fall within a 1-hour period, so Bob also receives an alert. Both Alice and Bob meet the criteria, so the output is Alice, Bob. This demonstrates how multiple employees can appear in the result if they each meet the alert condition. In the third example, John used his keycard at 23:58, 23:59, and 00:01. While these times are close together, they do not all fall within a single 1-hour period because the 1-hour window cannot wrap around midnight. Therefore, John does not receive an alert, and the output is an empty list. This highlights how the 1-hour window must be fully contained within the same day and cannot span across 2 days. Finally, let's discuss the constraints and edge cases. The input size can be as large as 100,000 records, so your solution must be efficient enough to handle this scale. Edge cases include scenarios like having only one access record, which would result in no alerts, or multiple employees meeting the alert condition simultaneously. Another important edge case involves times that wrap around midnight, which do not qualify as being within the same 1-hour period. Your solution should account for all these situations and ensure the output is accurate and returned in lexicographical order. To begin solving this problem, we need to consider different approaches to identify employees who use their keycard 3 or more times within a 1-hour window. The brute force method is perhaps the most straightforward to understand. Here, we iterate through all the keycard usage records, grouping the swipe times by employee and sorting them in ascending order. Once sorted, we check every possible triplet of swipe times for each employee to determine if they fall within a 1-hour window. While this approach ensures correctness, it is computationally expensive. Since we are using nested loops to examine all possible combinations, the time complexity grows cubically with the number of records, making it n cubed. Additionally, it requires extra space proportional to the number of unique employees for grouping. This makes the brute force method impractical for large datasets but useful as a baseline for understanding the problem's requirements. A more optimized solution is the sliding window technique, which avoids the inefficiencies of the brute force approach. First, we group the swipe times by employee and sort the times for each employee. Then, instead of checking all possible triplets, we use a sliding window to dynamically evaluate swipe times. Starting with the first swipe, the window expands to include additional swipes. If the time difference between the earliest and latest swipe in the window exceeds 60 minutes, the window is adjusted by moving the starting point forward. When 3 or more swipes are found within the window, an alert is triggered for that employee. This approach significantly reduces redundant calculations. Its time complexity is O, n log n, where sorting dominates, and the space complexity is O, k plus n, accounting for the group data and sorted swipe times. Alternatively, a binary search approach can be employed, which eliminates the need to explicitly slide the window. Instead, it uses binary search to locate the latest swipe time that satisfies the 1-hour condition for each starting swipe. However, this method introduces additional complexity due to repeated searches. The sliding window technique was chosen as the optimal strategy because it strikes the best balance between simplicity and efficiency. The brute force approach, while easy to implement, is prohibitively slow for larger datasets due to its O, n cubed, time complexity. On the other hand, the binary search approach, though efficient, is slightly more challenging to implement and does not provide a significant advantage over the sliding window method in terms of performance. With a time complexity of O, n log n, the sliding window approach achieves comparable efficiency to binary search but with simpler logic, making it easier to maintain and debug. A key insight that simplifies the problem is recognizing that sorting the swipe times for each employee allows us to focus only on swipes within the same 1-hour window. The sliding window is particularly effective here, as it avoids recalculating conditions for overlapping swipes, making it a natural fit for this problem. When comparing the trade-offs of these approaches, the brute force method stands out for its simplicity but is ultimately too inefficient to handle large datasets effectively. The sliding window method, in contrast, offers an excellent balance of simplicity and performance, making it both efficient and easy to implement. While the binary search approach matches the sliding window's efficiency, it adds implementation complexity that may not be necessary unless the dataset is extremely large and performance is absolutely critical. Overall, the sliding window technique is the preferred choice for this problem. It is efficient, maintainable, and aligns well with the problem's requirements, making it the most practical solution for detecting alerts based on keycard usage patterns. The problem requires us to analyze a list of keycard swipe records to identify employees who used their keycards 3 or more times within any 1-hour window. Each record consists of an employee's name and the time of the swipe in HHMM format. To solve this, we need to return a list of such employees along with the specific swipe times that meet the condition. The first step in the algorithm is to parse the input data by grouping the swipe records for each employee. This allows us to focus on one employee at a time, simplifying the subsequent logic for detecting valid 1-hour intervals. To achieve this, we use a dictionary where each key represents an employee's name, and the associated value is a list of that employee's swipe times. For example, given the input, Alice, 9 o'clock, Bob, 9:05, Alice, 9:30, Alice, 10 o'clock, we group the data as Alice, 9 o'clock, 9:30, 10 o'clock, Bob, 9:05. This structure ensures we can process each employee's data independently in the following steps. Now that we've grouped the data, the next step is to sort the swipe times for each employee. To do this, we first convert the times from their HHMM format into minutes since midnight. This numerical representation makes it easier to perform calculations and comparisons. The conversion uses the formula minutes equals hours * 60 plus minutes. For instance, 9 o'clock becomes 540, 9:30 becomes 570, and so on. Once converted, we sort the times in ascending order for each employee. For example, Alice with swipe times 9 o'clock, 9:30, 10 o'clock would have the times represented as 540, 570, 600. Sorting ensures the times are in chronological order, which is essential for applying the sliding window technique in the next step. The sliding window approach will allow us to efficiently identify whether 3 or more swipes fall within a 1-hour period for each employee. Using this sorted format avoids unnecessary complexity when iterating through the times. With the sorted swipe times, we can now apply the sliding window technique to efficiently detect 1-hour intervals containing 3 or more swipes. This involves using 2 pointers, start and end, to represent the boundaries of the window. Initially, start is set to 0, and we iterate end from 0 through the list of swipe times. At each step, we check if the difference between the swipe times at end and start exceeds 60 minutes. If it does, we increment start to shrink the window. If the size of the window, calculated as end start plus 1, reaches 3 or more, we record the employee and the swipe times within the window. For example, for Alice with times 540, 570, 600, the window 540, 570, 600 is valid because the difference between 600 and 540 is within 60 minutes. Once we identify valid windows, the results are formatted as a list of tuples containing the employee's name and their swipe times in a readable HHMM format. For example, 540, 570, 600 would be converted back to 9 o'clock, 9:30, 10 o'clock. This ensures the output clearly communicates which employees and times triggered the condition. The time complexity of this algorithm is O(n) log n, where n is the total number of swipes. This is primarily due to the sorting step for each employee's swipe times. The sliding window traversal itself is linear for each employee, so the sorting step dominates the overall complexity. The space complexity is O(n), as we use a dictionary to store the group swipe records and a list for the results. There are also opportunities for optimization, such as exiting early during the sliding window traversal if the window size exceeds 3. Additionally, using a deque for the sliding window can minimize adjustments to the pointers, further improving efficiency. By leveraging these techniques, we ensure the solution is both time efficient and space efficient while maintaining clarity and correctness. This approach handles edge cases like employees with fewer than 3 swipes, multiple swipes at the same time, or swipes spanning across midnight, ensuring the algorithm is robust and reliable. Here, we begin by importing the default dict class from Python's collections module to efficiently group swipe times by employee names. Inside the solution class, the alertNames method takes in 2 lists, keyName, which contains the names of employees, and keyTime, which contains the corresponding swipe times in HHMM format. We use a default dict to create a dictionary where each employee's name maps to a list of their swipe times. For each pair of name and time in the input, we convert the time into total minutes since midnight for easier computation. This value is then appended to the corresponding employees list in the dictionary. Next, we initialize an empty list called alerted_employees to store the names of employees who trigger an alert. For every employee in the dictionary, we sort their swipe times in ascending order. By iterating through the sorted times, we check if any 3 consecutive swipes fall within a 60-minute window. This is done by comparing the difference between the first and third swipes in each triplet. If the condition is met, the employee's name is added to the alerted_employees list, and we break out of the loop to avoid redundant checks. Finally, once all employees have been processed, we sort the list of alerted names alphabetically for the required output format and return it. In this example usage, we pass 2 lists to the alertNames method. The first list, Alice, Bob, Alice, Alice, Bob, represents the names of employees swiping their key cards, while the second list, 12:01, 12:02, 12 o'clock, 12:03, 12:01, represents the corresponding swipe times. The method would process these inputs to determine if any employee swiped their card 3 or more times within a 1-hour window. For instance, Alice swiped her card at 12 o'clock, 12:01, and 12:03, which all fall within a 60-minute period. As a result, Alice's name would be included in the output list. This example demonstrates how the solution identifies and returns the names of employees who triggered the alert according to the problem's conditions. Here, we start by importing the necessary packages and defining our solution class. The method alertNames takes 2 arrays as input, keyName, which contains the names of the employees, and keyTime, which holds the corresponding swipe times. Our first step is to group the swipe times by employee name. To do this, we use a hash map where the key is the employee's name, and the value is a list of times converted into minutes. Each time is split into hours and minutes, and then converted to total minutes for easier calculations. The computeIfAbsent method ensures that each employee has an associated list, and we add the converted time to that list. After grouping the data, we initialize a list called alerted employees to store the names of employees who meet the alert condition. The next task is to check the swipe times for each employee, which we'll address shortly. Once we have the swipe times grouped by employee, we sort these times for each employee using collections.sort. Sorting is critical because it allows us to efficiently check for 3 swipes within a 60-minute window. Using a loop, we iterate through the sorted list of swipe times and examine a sliding window of 3 consecutive times. If the difference between the earliest and the latest time in this window is 60 minutes or less, it means the employee has triggered the alert condition. In that case, we add their name to the alerted employees list and exit the loop to avoid duplicate entries. After processing all employees, we sort the alerted employees list alphabetically to meet the problem's requirements. Finally, we return the sorted list of alerted employee names as the result. To solve this problem, the first step is to group the swipe times for each employee. Here, we are given the input array's key name and key time, which pair each employee's name with the corresponding time they used their keycard. Using a default int, we store swipe times as minutes since midnight for each employee. For example, Alice swiped her card at 12:01, 12:00, and 12:03, which translates to 721, 720, and 723 minutes, respectively. Similarly, Bob swiped at 12:02 and 12:01, which translates to 722 and 721 minutes. After processing all the data, we get the grouped records. Alice has times 721, 720, 723, and Bob has 722, 721. Next, we sort the swipe times for each employee to simplify the process of checking time intervals. After sorting, Alice's times become 720, 721, 723, and Bob's times become 721, 722. After grouping and sorting the swipe times, the next step is to check if any employee swiped their keycard 3 or more times within a 1-hour period. Starting with Alice, we compare the time intervals between her swipes. Her earliest swipe at 720 minutes and her latest within 3 entries at 723 minutes show a difference of just 3 minutes, which is within the 1-hour threshold. Therefore, we add Alice to the alerted_employees list. For Bob, we see that he has only 2 swipes, which is fewer than the required 3 to trigger an alert. Finally, we sort the alerted employees alphabetically, resulting in a list containing only Alice. This forms the output for this example. Now let's analyze another example where there are no alerts. Here, the input indicates that Alice swiped her card at 12:00, Bob at 13:00, and Charlie at 14:00. First, we group the swipe times for each employee. Alice has 1 swipe at 720 minutes, Bob at 780 minutes, and Charlie at 840 minutes. After grouping, we sort the swipe times, but since each employee has only 1 swipe, their sorted times remain the same, Alice with 720, Bob with 780, and Charlie with 840. Next, we check for alerts. Since none of the employees have 3 or more swipes, no alerts are triggered. The alerted_employees list remains empty, and after sorting, the final output is an empty list. In this example, we deal with multiple employees in scenarios where some of them trigger alerts. Looking at the input, Alice swiped her card 3 times at 12:01, 12:02, and 12:03, while Bob swiped his card at 12:00, 12:30, 12:31, and 12:59. First, we group the swipe times by employee. Alice's times are converted to minutes as 721, 722, and 723. Bob's times are converted as 720, 750, 751, and 779. After grouping, the employee_records dictionary is populated with Alice's times as 721, 722, 723, and Bob's as 720, 750, 751, 779. Then, we sort the swipe times for each employee. The sorted times for Alice remain 721, 722, 723, and for Bob, they become 720, 750, 751, 779. After sorting the times, we check for alerts. For Alice, the difference between her earliest and latest swipe within 3 entries is 723, 721 equals 2 minutes, which is within the 1-hour limit. This means Alice triggers an alert and is added to the alerted_employees list. For Bob, we compare the intervals between his swipes. 751, 720 equals 31 minutes and 779, 750 equals 29 minutes are both within the 1-hour window. Since Bob has at least 3 swipes within a 1-hour period, he is also added to the alerted_employees list. Finally, we sort the alerted employees alphabetically, resulting in the list Alice, Bob. This is the output for this example. To analyze the time complexity of our solution, we start by breaking the process down step by step. First, we group keycard swipes by employee name. This is done using a loop, where we iterate through all the keycard swipes once. If there are n swipes in total, this grouping operation has a time complexity of O(n). Each individual operation within this step, such as extracting hours and minutes, converting them to total minutes, and appending the time to a list, takes constant time, or O(1). As a result, this entire grouping process remains O(n). Next, we sort the swipe times for each employee. Let's assume there are m unique employees. For any given employee, if they have k_i swipes, sorting their swipes takes k_i log k_i. When we sum this sorting cost across all employees, we get a total of k_1 log k_1 plus k_2 log k_2 plus k_m log k_m, where the sum of all swipes across employees equals n. In the worst case, if all swipes belong to a single employee, this simplifies to n log n. Finally, we check for 3 swipes within a 1-hour window. For each employee, iterating through their sorted swipe times has a time complexity of k_i. When summed across all employees, this step also totals n. We now discuss the time complexity of sorting alerted employee names alphabetically. Sorting a list of alerted employees takes log a, where is the number of names in the list. In the worst case, a could equal m, the total number of unique employees. Thus, this sorting step has a complexity of m log m. When we combine the time complexities of all the steps, we have n for grouping keycard swipes, n log n for sorting swipe times, n for the 1-hour window check, and m log m for sorting alerted names. The overall time complexity is dominated by the n log n term from sorting swipe times, making the final time complexity n log n. Now, let's consider the space complexity. First, we account for the storage of employee records. Swipe times for each employee are stored in a dictionary. In the worst case, all n swipes need to be stored, resulting in n space. The alerted employees list, which stores up to m names, requires m space. Together, these contribute to the overall space complexity. Sorting operations also require auxiliary space, so let's examine their contributions to the overall space complexity. When sorting the swipe times for each employee, we use additional space proportional to the number of swipes for that employee. This means sorting contributes k_i auxiliary space per employee. Summing across all employees, the total auxiliary space for sorting swipe times is n. Similarly, sorting the alerted employee names alphabetically requires additional space proportional to the size of the list, or m. Combining these factors, the total space complexity of the solution is n, which is dominated by the storage of swipe times. In comparison to a brute force approach, our solution is much more efficient. The brute force method involves directly comparing each employee's swipe times in all possible combinations of 3 swipes. This would result in a time complexity of n cubed, in the worst case, where all swipes belong to one employee. By pre-processing the data and leveraging sorting, we reduce the problem to n log n, which is a significant improvement. Now, let's analyze the algorithm in terms of best, average, and worst-case scenarios. In the best case, if no employee has 3 or more swipes, the 1-hour window check is skipped entirely. Here, the complexity is dominated by the sorting step, resulting in n log n. In the average case, where employees have varied numbers of swipes, the complexity remains n log n, because sorting still dominates. For the worst case, if all n swipes belong to a single employee, we must sort all the swipes and perform the 1-hour window check for these n entries. Even in this scenario, the time complexity remains n log n. This consistency across different scenarios demonstrates that the algorithm is efficient and scales well, especially when compared to the naive approach, which has a much higher time complexity of n cubed. When solving this problem, there are a few common mistakes to watch out for. First, failing to sort the keycard usage records by time for each employee is a significant issue. Sorting is essential because the sliding window logic depends on having the records in sequential order. Without sorting, your solution might miss valid cases or produce incorrect results. Another frequent mistake is using inefficient nested loops to check all combinations of records. This brute force approach can lead to an O(n)² time complexity, which becomes impractical for large datasets. Lastly, many developers overlook critical edge cases. For example, what happens when an employee only has 2 records? Or when exactly 3 timestamps fall within the same 1-hour window? Ignoring these scenarios can result in errors, so it's important to handle them carefully. Another pitfall to avoid is hard-coding time comparisons. Instead of directly comparing timestamps in a fixed way, it's better to convert times into a uniform format, like minutes, to allow for dynamic calculations. Hard-coding reduces flexibility and makes your solution less adaptable if you need to change the time window. Additionally, overcomplicating the sliding window logic is a common issue. Some solutions use unnecessarily complex data structures, like priority queues or hash maps, to track time intervals. These can make the code harder to debug and maintain. A simpler sliding window approach, often implemented with 2 pointers, is both efficient and easier to manage. Simplifying your logic can help avoid bugs and make it easier to address edge cases. This problem is an excellent opportunity to demonstrate your understanding of the sliding window technique, which is a common pattern for solving time-based problems. Recognizing when to apply this approach is a key skill, especially in interviews. Interviewers often focus on how you optimize your solution, so be prepared to explain how you transition from a brute force O(n)² approach to a more efficient O(n)log(n) solution. It's also important to emphasize edge case handling, such as testing scenarios with exactly 2 records or closely spaced timestamps. Lastly, you should be ready to discuss the time and space complexity of your solution. Highlight the trade-offs between different approaches and explain why you chose a particular algorithm or data structure. To strengthen your understanding of this problem, it helps to explore related problems on LeetCode. For instance, LeetCode 56, Merge Intervals, involves sorting and merging overlapping intervals, which is similar to managing time windows. LeetCode 253, Meeting Rooms 2, deals with counting overlapping intervals, another problem with structural similarities. Additionally, LeetCode 3, Longest Substring Without Repeating Characters, uses the sliding window technique to find substrings, showcasing its versatility. Finally, LeetCode 30, Substring with Concatenation of All Words, provides another example of how to dynamically adjust a sliding window while managing substrings. These problems can help you recognize patterns and refine your skills with sliding window approaches. When considering alternative approaches, the brute force method involves comparing all possible combinations of 3 timestamps for each employee. While simple to implement, it's highly inefficient with a time complexity of O(n)² or worse, which makes it impractical for large datasets. A more optimized approach is to sort the records by timestamp and then use the sliding window technique to identify valid time intervals. This method is efficient, with a time complexity of O(n)log(n) due to sorting, and it handles edge cases effectively. Another option is to use a hash map to group records by employee before sorting and processing each group. This maintains the same O(n)log(n) efficiency but simplifies the logic for grouping records. Each approach has trade-offs, so it's important to choose the one that balances simplicity, efficiency, and clarity for the given problem constraints. Great job! To recap, we tackled problem number 1604 and reviewed a brute force approach to detect suspicious keycard usage within a 1-hour window. Key takeaways include understanding time-based filtering techniques and balancing efficiency with correctness. Thanks for watching, and don't forget to like and subscribe for more coding challenges. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!